So here we are at chapter 5. So we've gone through sort of the golden age of Greek mathematics. That was during the time of Euclid and Archimedes, 3rd century BC, 2nd century BC. And I guess it was around 146 BC that something happens, and the Greek kingdom of Egypt, that would be the Ptolemaic kingdom. Ptolemy the Seventh, who was the Pharaoh of Egypt, he was actually a Greek king, but he would have declared himself Pharaoh of Egypt, one of the many Ptolemies of the Ptolemaic kingdom, banished many scholars and philosophers that he did not think were very loyal to him. So he kind of had this paranoia about people not being loyal to him. So this was in 146 BC. So we're going to write here the decline of Greek mathematics. So one big event that began this, kicked this off, was Ptolemy VII. Banished scholars. Remember, all the scholars came to the city of Alexandria. Alexandria was kind of the big hub for intellectuals of that time. Alexandria was in northern Egypt on the Mediterranean. And all the Greek scholars and philosophers would come there to study at the Library of Alexandria, which was actually a university, you could say. So Ptolemy banished scholars who he did not think were loyal to him. He was paranoid. This was 146 BC. So this caused many intellectuals who already were there and weren't banished to avoid Alexandria. So intellectuals left Alexandria. Also, during this time in history, we have the rise of Rome. So Rome was a city in Italy. It was actually a republic that was ruled by the Senate and some different other political leaders called consuls. And Rome began to gain power. It began to conquer its neighbors. It started the conquest of various Greek kingdoms in the 100s BC. But Rome had fully conquered all the different Greek kingdoms. So Greece itself proper was split up in different kingdoms, and then you had the different Greek kingdoms in the Middle East and in Egypt. So Ptolemaic Egypt was conquered. That's where Alexandria was, the center of learning. Ptolemaic Egypt. And of course, Alexandria in particular was conquered by Rome in 31 BC. So Alexandria was conquered with Mark Antony and Cleopatra. You've heard of maybe Cleopatra before. She was the last Greek ruler of Egypt. She and her lover, who was a Roman, they lost the war against who? Octavian, right? Octavian was Julius Caesar's nephew. So Octavian conquered Egypt, and it became a Roman province inside the Roman Republic. And shortly thereafter, it became the Roman Empire. Well, here we are at 31 BC. So essentially, Alexandria becomes part of the Roman Empire, and the Roman culture has sort of different values, different cultural values than the Greek culture. So Roman cultural values are different than Greek cultural values. Emphasizing the practical over the theoretical. So the Greeks were very much interested in scholarship, the theoretical. Mathematics, for example, is very theoretical. The Romans, they were more into like engineering. They were more into law. They were into oratory, public speaking, that kind of thing, politics, studying those sort of things. So, the Romans themselves didn't really create a lot of mathematicians. So, Alexandria continued on under the Roman Empire, but there was a general sort of decline in the intellectual content produced there at Alexandria. Also, another big thing that happened was the rise of Christianity. This was under the Roman Empire. So Christianity was a religion from the Middle East that spread all throughout the Roman Empire. And initially, Christians were persecuted. Initially, Christians were persecuted. And because of this persecution, they had a very kind of bad feeling towards the Romans. So the Christians developed bad feelings towards the Romans. Viewed Romans in a bad way. And at some point, we have that the Christians become almost a majority in the Roman Empire. And there's a Roman Emperor, Constantine, who essentially makes Christianity a fully acceptable religion, a tolerable religion. And Christianity eventually becomes the official religion of the Roman Empire at some point. So Christians believed in faith rather than reason. So, because Christians primarily believed in faith and they were somewhat against reasoning, this kind of attitude contributed to, not producing a lot of intellectuals from the Christian tradition. There were some intellectuals, but they wrote mostly about faith rather than anything mathematical or philosophical so much, or scientific. During this time period, the decline of Greek mathematics, one of the great mathematicians, geometers, actually astronomer, was Claudius Ptolemy. Claudius Ptolemy, he was from 100 AD. This is during the time of the Roman Empire to 170 AD. So his last name is Greek, right? Ptolemy. First name, Claudius, that is Latin. So it was a Latin and a Greek name mixed together there. So he is considered the greatest astronomer of antiquity. Antiquity is ancient times. He wrote a very famous work known as Syntaxis Mathematica. Syntaxis Mathematica, which often you'll hear it called the Almagest. So Almagest is not actually the name that he gave. The name he gave was Syntaxis Mathematica. Almagest is a word given to it by the Arabs. So the Arabs later named it the Almagest, which means the greatest. The greatest in Arabic. So after the Roman Empire collapses and much of the ancient knowledge was lost to the Europeans, the Arabs came and they found a lot of these books and they took them back to Baghdad and they read these books and they were so impressed with these books. Their wise men read them and they found this one particularly great and they called it the greatest. So what is Syntaxis Mathematica, or the Almagest? It's actually a book. It's considered a masterpiece of astronomy, which is a masterpiece in astronomy and geometry. It's considered the most influential astronomy text in history, and it was sort of the gold standard for astronomy text up until sort of the Renaissance of the 1400s. So over more than 1,000 years, almost 1,300 years. Yeah. So there's one major problem with it, and that's because it had a Earth-centric view, a geocentric model of the Earth, geocentric model of the universe. So the view was that the Earth was at the center of the universe, and then you had the sun that went around the Earth, and you had other planets going around the Earth after the sun. So today, it's not really studied anymore, but at one point in history, it was studied all the way up until the 1400s. And now, of course, we know that the Earth is not the center of the universe. We know we have a solar system, and the sun is the center of the solar system. The Earth goes around the sun. So in this book, we have a lot of astronomy and a good deal of geometry as well, because the astronomy is expedited, or I should say, it's shown through geometry. So here's a famous theorem in geometry from Ptolemy. We're going to call this Ptolemy's theorem. Ptolemy's theorem says if ABCD is a quadrilateral inscribed in a circle, let's draw a picture. Here I have my circle, and here I have my quadrilateral. Let's call this one A, B, C, D. And And here are our diagonals. So if ABCD is a quadrilateral inscribed in a circle, then if I take the product of the diagonals, AC and BD, multiply those together, right? So we got AC times BD. That's going to be these two sides multiplied plus these two sides multiplied. So the green sides multiplied plus the blue sides multiplied. So that would be BC times AD plus AB times CD. Ptolemy's theorem right here. Very useful theorem. So here's a little exercise. So what we're going to have a circle, and inside this circle we're going to have a pentagon, a regular pentagon, so a regular 5-gon, with a pentagram inscribed inside. And we're going to call this side right here B, and this side right here little a. So we got A, B, C, D, E. So what we want to show, our goal is to show that BE over AB equals the golden ratio, 1 plus the square root of 5 over 2, the golden ratio. So to prove this, okay, I'm going to do a proof here. I am going to focus on this quadrilateral involving ABDE. This yellow quadrilateral ABDE. So in this quadrilateral, this yellow quadrilateral, we have basically two sorts of lengths. We have the long diagonal like BE, which is little a, and AD, which is little a. Also we have the long sides BD, which is going to be little a. And I think that's it. And then we got little b, which is AB, AE, and DE, little a. So let's start with taking the product of the diagonals of this quadrilateral. So I got this one and this one. So according to Ptolemy's theorem, I'm going to have AD times BE. That's going to be equal to, let's see, the product of these two red sides, AE times BD, plus, get a different color, purple, or violet. The product of these two sides here, it's going to be AB times DE. All right, now what's another name for AD? AD, that's little a. What about BE? That's little a. What about AE? AE is little b. What about BD? That's going to be little a. What about AB? That's little b. What about DE? That's little b. So I end up with a squared equals BA plus B squared. I'm going to divide everything by B squared. If I divide everything by B squared, I'm going to get A over B in parentheses squared equals, the B's cancel, I get A over B, and here I can write B squared over B squared as 1. So rewriting this, I get A over B squared minus A over B minus 1 equals 0 as a quadratic So imagine I have a quadratic where my variable rather than x is a over b. So to solve this quadratic, I have a over b equals minus -1 plus or minus the square root of -1 squared minus 4 times 1 times -1. That's using the quadratic formula, all over 2 times 1. Now keep in mind that we can't do the minus here. Remember, you have a plus or a minus. Sorry, can't get this to work. It's supposed to be red here. Right, I have a plus or a minus here. I can't do the minus. See that red minus sign right there? I can't do that because if I minus, I'll end up getting a negative. Remember, a over b is a ratio, right? A over b is a ratio of this side to this side, and that has to be a positive number, right? If you take a positive length over a positive length, you get a positive length, or a positive ratio. So I can't do this minus here, this red minus sign. I'm going to delete that. I'm just going to end up here with having a plus. If I write this out nice, I get a over b equals +1 plus square root of -1 squared is 1, and when I multiply -4 times 1 times -1, I get +5. All that's over 2. Oh, sorry. That's going to be 4, right? 4, right? -4 times 1 times -1 is +4. So that means a over b is 1 plus square root of 5. 1 plus 4 is 5 over 2. And that's the golden ratio. And a proof. That's really interesting. So we have a over b is the golden ratio. Remember, a was be, or in other words, be over ab. So 1 plus the square root of 5 over 2, the golden ratio. Yeah, they actually wrote be over ab, right? Be over ab, that's a little a over little b. Let me delete that, there, that box, okay. And I'll put this at the end of my proof here. Cool. That's really cool. So if I'm dealing with one of those regular pentagons, that means the long side there over the short side is always the golden ratio. All right, who else do we want to talk about? We want to talk about Claudius Ptolemy and his work Syntaxis Mathematica, Book of Astronomy. The next guy we want to talk about is Diophantus. Diophantus. He's sometimes called the father of algebra. So he was from roughly, so when you see C, that means roughly, so circa about 280 to about 280 AD. So he was a Hellenized Babylonian. What does Hellenize mean? Hellenize means, well, he was Greekized. Hellenized. So Hellenic refers to Greek. So he was a Babylonian of Greek culture. So he lived in Alexandria, city of Alexandria. And he wrote a great work, which we know today as Arithmetica. Wrote Arithmetica, which was the first treatise on algebra. So we know the Egyptians did a little algebra. The Babylonians did more advanced algebras for like quadratic equations. But this guy wrote the first true treatise on algebra. And he was the first one to have a symbolic treatment of algebra. So first symbolic treatments of algebra. So before, when equations were solved, people would just write out paragraphs and say, okay, we're going to add a number to both sides, we're going to subtract a number, and we're going to square both sides or something like that. So they would have written that in paragraphs. So he actually wrote out symbols. Nothing like ours, but apparently for unknown quantities, he used the zeta symbol. This would be like our variable x. And if he wanted to square an unknown, he would have written delta with a superscript gamma. Square of an unknown quantity. If he wanted a cube of an unknown, he would have taken kappa with a superscript gamma. Cube of an unknown. If he wanted a fourth power of an unknown, he would have put a delta superscript gamma delta. Fourth power of unknown. This symbol was his minus. And the iota symbol looks like an I without a dot. This is the equal sign. Apparently he did not have an addition symbol. That's what I'm reading here. So for example, if I were to write this, kappa superscript. It's my cat, Scratchy. Give me a kiss, boy. He's kissing all over me. All right, he's on my pad. All right. If I wrote kappa superscript gamma, lambda, epsilon. This would mean right here, this would be x cubed. This would be 35. So we would have, this is 35x cubed. So just a little sampling of some of his symbols that he would have used. So I guess what we want to do, we want to work a few problems from Diophantus's Arithmetica. Some problems from Arithmetica. See if we can pick out a few problems. Okay, so here's an exercise. Number 1. This is from book 1, problem 28. Don't scratch, don't scratch, don't scratch. You're gonna hurt yourself. Find two numbers. Such that their sum and the sum of their squares are given numbers. Say their sum is 20 and the sum of their squares is 208. Okay. So to solve this, let A and B be the numbers. So first of all, their sum, A plus B, has to be 20, right? And second of all, sum of their squares, A squared plus B squared, has to be 208. So we have a system of equations. All Alright, so what I'm going to do, I'm going to actually square equation 1 and take a plus b and square that. So a plus b squared is going to be, we know, 20 squared. Now if I write out a plus b times a plus b, I'm going to have, that's 400, right? 20 squared is 400. Well, if I FOIL out a plus b times a plus b, I'm going to get a squared plus 2ab plus b squared. That's going to be 400. Now mind here that a squared plus b squared, remember a squared plus b squared is 208. So I'm going to replace a squared plus b squared here with, so I got 208 plus 2ab equals 400. And now I can subtract 208 from both sides. So I'll get 2ab equals 400 minus 208 is simply 192. Oh, and then I can divide both sides by 2 here. And I'll get that AB as 96. So if I take this up here, I have a plus b is 20, and a times b is 96. So all I have to do is solve here for a and b. This is the Babylonian style. Remember way back in our first unit on Babylon, our first exam. So when you have a system of equations where you have a sum is a number and you have a product as a number, you're going to let x be, how does it go? We're going to take this 20 here over 2 plus c, and then for y, we're going to take that number again, 20 over 2 minus c. The first thing we want to do is check if x plus y is equal to 20. Well, let me first reduce it. So, right, this is what? 20 over 2 is 10. So I got 10 plus c is x. For y, 10 minus c. Okay, so now we want to check. Let's see, if I take x plus y. Okay. Sorry, I shouldn't be using x and y. I should use an a and b. So let me go back and replace my x's with a's. If I can get this to work. There goes. And my y's I'm going to replace with b's. There we go. Okay. Better. Better. So I got to check that my a plus b is 20. So my a plus b is what? 10 plus z plus 10 minus c. So notice that z and the minus z cancel, and I get 10 plus 10 is 20. So that checks. I got to do my product, a times b, right? That has to be equal to 96. Now, remember a we have is 10 plus c, and b is 10 minus c. So when I do the 10 plus c times 10 minus c, when I FOIL those out, I'd say I got a difference of squares, right? 10 plus c, 10 minus c, that's going to be 100 minus c squared. Equals 96. So I'll get 100 minus 96 equals z squared. So 100 minus 96, that's 4. 4 equals z squared, and I take the square root. Z is 2. Magic. So plugging those back in, those z's back in, right? For my a and for my b, I'm going to get a is 10 plus 2, and for b, 10 minus 2. So I'm going to get a as 8, b, 12. A is 12. And my tools just messed up. My cat messed up my tools. So everything's sideways. There it goes. That's better. A is 12, B is 8. And that should check out, right? Because remember, the original equation, here we have 12 plus 8 is 20. And the next one we have what? 12 squared is 144 plus 8 squared is 64. That adds up to 208. Or you could do here 12 plus 8 is 20, and 12 times 8 is 96. Right there. Those are our two numbers, A and B. All right, so that's one of the problems. That's for Diophantus. Here's another famous problem. Book 1, problem 17. Find 4 numbers such that when any 3 are added together, their sum is one of the 4. Numbers. Say their given sums are 20, 22, 24, and 27. Okay, so we're going to call these numbers maybe A, B, C, and D. So let A, B, C, and D be the numbers. We got to find 4 numbers where when you add 3 of them together, one of the sums of the 3 is 20, one of the sums of the 3 is 22, one of the sums of the 3 is 24, and one of the sums of the 3 is 27. So we got to find A, B, C, and D. So let A, B, C, D be the numbers, and let X be the sum of all 4. So right now, we know when we add up 3 of them, let's say A, B, and C, we get 20. And we add up another group of 3, let's say A plus B plus D, we get 22. We add up another group, A plus C plus D, we get 24. And then we add up another group, the only one left is B plus C plus D. That's the only group of 3 left. B plus C plus D is 27. Do note with these 4 equations. If you look at the very first equation here, I'm underlining in red. Well, that's supposed to be red. Notice A plus B plus C equals 20. You're missing the D, right? You're missing the D. So if I look at this X right here, X has everything in it. Everything in it. So that first equation, I'm going to put a check by. That has everything except for D. So I can replace that with X minus D equals 20. And then the next equation I'm checking off, that's missing the C, so I can replace that with X minus C equals 22. And the next one I check off is missing the B, so I can write that as X minus B equals 24. And the last one I'll check off in violet, that's missing the A, so that's X minus A equals 27. So I'm going to rewrite this. I'm going to get X by itself on the left, so I get, let's see, X equals D plus 20, X equals C plus 22, X equals B plus 24, X equals A plus 27. So on the left side, I'm going to add all the X's. I'm going to get 4 X's. On the right side, I'm going to add all the A plus B plus C plus D, A plus B plus C plus D. I'm going to add 20 plus 22 plus 24 plus 27. When I add those together, let's see, what do I get when I add those together? I get 93. Now, if I take A plus B plus C plus D, remember A plus b plus c plus d is x. So this is 4x equals x plus 93. Now I subtract x from both sides. I'm going to end up with 3x equals 93. So dividing both sides by 3, I'll get x is 31. Now, remember, I got to find a plus b plus, I got to find a, b, c, and d, right? A, b, c, and d. A, b, c, and d. If I go back here, a is going to be x minus 27. B is going to be what? X minus 24. C is going to be x minus 22. And D is going to be x minus 20. Now we calculated x to be 31. So if I plug in 31 here, I get 31 minus 27 is 4 for A. For B, I'm going to get 31 minus 24, that's 7 for B. For C, I'm going to get 34 minus 22. 31 minus 22 is 9 for C, and for D, 31 minus 20 is 11. So we got 4, 7, 9, and 11. Yeah, 4, 7, 9, 11. So that's it. Those are my 4 numbers. All right, anything else interesting? Let's do a problem from book 2. Problem 12. This says find a number whose subtraction from 2 given numbers say 9 and 21 allows both differences to be squares. Hint. Here's a hint. Call the required number nine minus x squared. All right, so the idea is we're finding a number that we're going to take away from 9, and we're going to get a square. And we're going to take another number, that same number, away from 21, and we're going to get another square. So let's call that number A. Let A be the required number. And we're going to set A equal to 9 minus x squared. Right, we're told to set equal to 9 minus x squared. So that means 9 minus A should be a square. Let's see, 9 minus A is 9 minus x squared. Well, notice the 9's cancel when we get a positive x squared. And also, 21. 21 minus that number should also be a square. Let's see, 21 minus 9 minus x squared. That's going to give us 12 plus x squared. Well, that apparently is not obviously a square. Not obviously a square. So what we're going to have to do, we're going to have to choose x in such a way such that 12 plus x squared is a square. That's what we're going to do. So we're going to choose x. So x is going to have to be less than 9, not less than 9, choose x such that x squared has to be less than 9. Why does x squared has to be less than 9? If you think about it right here, x squared better be less than 9, because if you pick x squared bigger than 9, then 9 minus x squared is going to be a negative number, and we don't want negative numbers here. At this point in history, there was no concept of negative numbers in the Greek-speaking world. So we want to pick x squared to be less than 9, and we want to pick x such that x squared is less than 9, and such that 12 plus x squared is a square. So what could I pick x to be so that x squared is less than 9, and so that 12 plus x squared is a square? How about if I pick x to be simply 2? So pick x to be equal to, right? So if I took x squared, that would be 4, that's less than 9. And also, let's see, if I take 12 plus x squared, 12 plus 2 squared, I end up with 12 plus 4 is 16, which is a square, right? So let's finally note a will be 9 minus 2 squared, right? 9 minus x squared. So that's 9 minus 4 is 5. So a is 5. So let's check our work. So a should be the number. So a should be 5. Let's check our work. So 9 minus 5, that's 4, right? That's a square. And let's check 21 minus 5. That should be a square. That's 16. Yes, that's a square as well. Those are squares. So check, check. So here's our answer here. A is 5. All right, let's do one more problem for practice sake. This is number 4. Now this is similar. I think you actually get to do book 2, problem 10. So we're going to do one similar to book 2, problem 10. Not a hard problem, but I want to make sure I do one like it. So let's find 2 square numbers. Whose difference is 100. All right, so let's do that. So starting my solution, let alpha be a perfect square, x squared, and beta be a perfect square. Let's go x plus a squared. So we got 2 perfect squares. So the difference has to be 100. So beta has to be bigger than alpha here. Notice because x squared is smaller than x plus a squared. So when we subtract the bigger minus the smaller, beta minus alpha, we're going to get 100. Now if I replace beta with x plus a squared and alpha with x squared, that's 100. I can FOIL out, right, x plus a times x plus a. Right, if I FOIL that out here in red, that's going to give me x squared plus 2ax plus a squared, and then I have that's minus x squared equals 100. So here the x squareds are going to cancel. I'm going to get 2ax plus a squared equals 100. So what I want to do here, I want to choose a such that a squared is less than 100, right? We know for sure that a squared here has to be smaller than 100, because if a squared is equal to 100 or more than 100, then this whole thing right here, 2ax plus a squared, that's going to be way bigger than 100. We don't want it to be bigger, right? We want it to be equal. So I got to pick this a squared right here. If I can get it to right. This a squared right here to be, well, less than 100. So I want to find an a such that a squared is less than 100, and so that x comes out nice. So when we solve for x, it comes out nice. I figured out that I just played around with some numbers. So I tried 1, it didn't work out nice. Let's choose a to be 2 again. If a is 2, then I'm going to have the equation 2 times 2x plus 2 squared equals 100. That's just plugging in 2 for a. So we're going to get 4x plus 4 equals 100. Subtract 4 from both sides. I get 4x equals 96, and I can divide both sides by 4, and I get a nice value for x. It just works out nicely if you choose that value for a to be 2. So x equals, what is 96 divided by 4? That's 24. So x is 24. So let's plug that back in here and here to get our alpha and beta. So alpha, we said, was x squared, so that's 24 squared. So alpha is 576. And beta was what? X plus a. What was a? We have x is 24. A was 2. So 24 plus 2 squared. So beta is 26 squared. What is that? 676. So yeah. Alpha is a perfect square. Beta is a perfect square. And when you take the difference, right? When you take the difference, 676 minus 576, you end up with 100. That was the goal. All right, so anything else we want to say? I don't think we'll work any more problems. We'll just talk a little more about the twilight of Greek mathematics. So kind of the very end of the Greek period, the Western and Eastern Roman empires. So basically the empire was divided into a Western and an Eastern Roman Empire. First split in 285. So there was a Roman emperor by the name of Diocletian who split up the Roman Empire to make it easier to manage. And that was in 285, and again it fully came apart into 2 separate empires in 395 AD. That was under Honorius. So the first subdivision wasn't a full dividing of the empire. It was just kind of subdividing it up to make it easier to manage. But the second time it fully split, and there were 2 independent empires, a Western and an Eastern Empire. So this is signaling the end of the Roman Empire. So things became very turbulent, and anytime there's kind of political turmoil, things become uncertain, and there's less usually scholarship and things of that nature going on. And there's a lot of political turmoil. So during this time period, we have a mathematician by the name of Pappus from roughly 290 AD to 350 AD. He wrote the Mathematical Collection. This is consisting of 8 books that consolidate the knowledge of geometry of this time. He also wrote commentary on Claudius Ptolemy's Syntaxis Mathematica, also known as the Almagest. Okay, finally we come to our last mathematician of this declining period of Greek mathematics, Hypatia. This is the first woman mathematician that we know of in history, 370 to 415 AD. The Roman Empire is coming apart. It's been invaded multiple times by barbarians, as they call them, people from Germania, the Germanic tribes, and Huns from Central Asia. There are a lot of civil wars happening, so the empire is coming apart. Things are really turbulent politically. So here we have Hypatia. She was of Alexandria. She was the first woman mathematician known to history. Her father was Theon of Alexandria. Father was Theon of Alexandria, an astronomer. Her father was a very respected astronomer at the museum, or the Library of Alexandria, whatever you want to call it. And she learned from him. So she was a Neoplatonic philosopher. At the Library of Alexandria. As far as we know, she didn't create any original work of her own, but she wrote commentary on Diophantus's Arithmetica. On Apollonius's conic sections. And she edited Syntaxis Mathematica, the Almagest. So she was a pagan. She worshipped the Greek gods. She was a Greek pagan. And at this time, pagans were persecuted by Christians. So in Alexandria, there was a lot of sort of ethnic and religious division, a lot of tension, and the Christians became kind of dominant at this time, and they started persecuting the pagans, were persecuted by Christians. In particular, she was charged with spreading paganism. That was her charge. So there was a Christian mob who went around, and they saw the pagans as, the scholars and the mathematicians, the philosophers, as practicing this kind of weird mysticism. They thought mathematics was some kind of pagan mysticism, and they thought anyone who taught mathematics was spreading paganism. So, because she was a teacher of mathematics and philosophy, she spread paganism. So she was charged with that, and a Christian mob murdered her. They dragged her through the streets, and they basically cut her to death with seashells, and she died there. So, was murdered by an angry Christian mob. So during this incident, when she was dragged from the Library of Alexandria through the streets, the Library of Alexandria was looted and plundered. Library of Alexandria. Looted and plundered by Christian mob. So many documents, many books were destroyed in this incident. And this would have been in 415 AD. This was a very unfortunate incident where much was probably lost at the Library of Alexandria. And it would eventually be burnt to the ground in 641 AD, roughly 130 years later, roughly, by the Arab Muslims. So later, more than 200 years later, the Arab Muslims come through, and the Arabs, they invade Alexandria, and they burn the museum to the ground, the library to the ground, and all is lost. But this is essentially the end of the Roman Empire and the end of Greek mathematics.